So if you watched your friend fall into a black hole, you'd never actually see them cross the edge, which is just a completely wild thing to think about.
Right, yeah. To your eyes, from a safe distance, they would just sort of, slow down and freeze in place, and then slowly fade to dark red until they just disappeared entirely.
It's basically the ultimate optical illusion. Welcome to the deep dive, everyone.
Yeah.
Today we have a really densely packed brief in front of us, document 14.
Yeah, it's a fantastic overview detailing the modern astrophysics of black holes.
And our mission today is to, well, strip away all those Hollywood sci-fi tropes.
Yeah.
We really want to break down the actual mind-bending physics of these objects for you.
Exactly. We're going to cover their violent births, the extreme mechanics of their anatomy, and the absolute paradoxes they create.
So whether you are just insanely curious about space or you're trying to catch up on modern astrophysics, we want you to truly appreciate what happens when gravity basically breaks the universe's rulebook, and to do it without feeling overwhelmed by all the dense science.
And I think to really understand these objects, the first thing we have to do is unlearn a really persistent pop culture myth.
Oh, the cosmic vacuum cleaner myth.
Yes, black holes are not cosmic vacuum cleaners. They don't just, roam the galaxy aggressively sucking up space like a giant drain.
Right, they aren't just giant empty holes either.
Exactly. They're incredibly compact, localized objects with enormous gravity. I mean, if you magically compressed our sun down into a black hole of the exact same mass, Earth's orbit wouldn't change by a single millimeter.
Wait, really? Not a millimeter?
Nope. We would freeze, obviously, because the light and heat would be gone, but we wouldn't get pulled in. The gravitational force acting on us from this distance would be completely identical. It's all about density, not just mass.
Okay, so the danger really only exists if you wander way too close.
Yeah.
But the physics of how you actually get that kind of localized extreme density in the first place is, well, it's fascinating.
It really is. It basically requires a total failure of physical equilibrium.
Which makes sense. I mean, for millions of years, a massive star is essentially this incredibly delicate balancing act.
Right. You can think of it like a giant industrial pressure cooker.
Okay, let's unpack this for a second. Imagine the star is like a balloon. You have this immense outward pressure generated by the nuclear fusion at the star's core. That's the air inside the balloon.
And that outward pressure is perfectly balancing the inward pull of gravity, which is the rubber of the balloon constantly trying to snap shut.
Exactly. That equilibrium keeps the star stable. But the fuel isn't infinite, right?
No, it's not. The nuclear reactor at the core eventually runs out of hydrogen and heavier elements. And when that fusion process stops, the outward pressure just drops to zero.
In like a fraction of a second, right?
Yes. With the release valve sealed and the internal pressure suddenly gone, gravity wins instantly. The entire mass of the star collapses inward at a significant fraction of the speed of light.
Just boom. The core crushes down into a singular point, and the outer layers of the star hit that dense center and rebound outward in a massive supernova explosion.
Which is one of the most violent events in the universe. But if the remaining core is massive enough, what's left behind is our black hole.
So let's follow the material that didn't get blown away in the supernova. Let's take a hypothetical journey toward that new black hole. Far before you ever reach the center, you encounter the outer anatomy, right?
Yeah, starting with the accretion disk and the jets. Because, any matter that survived or gets pulled into the immediate area doesn't just fall straight down.
Because everything in space is already spinning.
Exactly. Everything has some rotational momentum. So the matter begins to spiral inward. And as this gas and dust rush toward the center, orbital mechanics basically force it to collide with itself.
Flattening out into this swirling structure.
Right, that's the accretion disk.
And because that matter is just crowding together so tightly as it spirals closer, the friction must be completely incomprehensible.
Oh, it is. The magnetic fields are twisting, particles are literally grinding against each other, and the gas in that disk heats up to millions of degrees.
Which is such a wild paradox. The darkest objects in the universe, these things that trap light, are actually surrounded by the brightest, most luminous material we can observe.
They shine brilliantly across the cosmos. It's how we find them. And what's fascinating here is that the magnetic fields winding through that superheated plasma are so intense they actually channel a portion of that infalling material away.
Away from the center.
Yeah. Before it can cross into the black hole, these magnetic highways accelerate the particles to nearly the speed of light and just blast them out into deep space from the poles.
Wow. And those are the astrophysical jets, right? The text mentions they can stretch for thousands of light years.
Exactly. But for the matter in the disk that doesn't get blasted out, it just spirals tighter and tighter until it hits the event horizon.
The infamous point of no return.
Yes, and it's important to note it's not a physical surface. You can't, touch it. It is purely a mathematical threshold in space where the escape velocity exceeds the speed of light.
And since light speed is the absolute speed limit of the universe, nothing can go faster.
Right. So once a particle or a rock or even a beam of light crosses that invisible boundary, it is permanently severed from the rest of the observable universe.
It's just trapped.
Trapped completely. Past the event horizon, the trajectory of space-time curves inward so severely that literally all possible paths just point toward the center.
And that center is the singularity.
Right. Our current physics suggests all that mass from the original collapsed star is compressed into a tiny point of infinite density.
And practically zero volume. It's just so hard to wrap your head around. And the sheer scale of these things forces us to categorize them, right? And the leap between the categories is pretty jarring.
Yeah, it really is.
So the source mentions stellar mass black holes, which we just described. Those run between 3 to 100 times the mass of our sun. But then you skip a few weight classes.
You skip the intermediate ones, yeah, which are hundreds to thousands of suns.
Right, and suddenly you hit the supermassive behemoths, millions or billions of times the mass of the sun. Here's where it gets really interesting for me.
Because these supermassive variants don't just wander around, right? They anchor entire galaxies.
Right, including our own Milky Way.
Exactly. If you look toward the center of the Milky Way, you'll find Sagittarius A.
Our very own galactic neighbor.
Yeah. It sits about 26,000 light years away, and it packs a staggering 4 million solar masses into a region of space that's actually smaller than our solar system.
Which is just, it's terrifying and amazing. And getting visual confirmation of that scale was a massive milestone. I remember reading in the text that in 2019, humanity finally got its first direct image of a black hole.
Yes, the Event Horizon Telescope collaboration. Though, to be clear, that first image wasn't our black hole. It was the supermassive one in the galaxy Messier 87.
Right, M87. But they didn't just point a regular optical telescope at the sky, did they?
No, they couldn't. They had to link up radio observatories all across the globe. It's a technique called very long baseline interferometry. They effectively turned the entire Earth into one giant telescope lens.
Just to capture the glowing accretion disk.
Exactly. Capturing those radio frequencies from the superheated gas allowed us to see the exact shadow cast by the event horizon, and it perfectly matched Einstein's predictions from over a century ago.
Which is a huge win for general relativity. But, I have a mechanical problem with this whole supermassive category.
What's that?
Well, if we establish that stellar black holes form from dying stars, there's a hard physical limit to how massive a single star can get before it just blows itself apart.
Right, you can't have a star the size of a billion suns.
Exactly. So if the universe is only 13.8 billion years old, there simply hasn't been enough time for a regular stellar black hole to slowly gorge on gas and merge its way up to a billion solar masses. So how in the world did they get so big so fast?
You've just isolated what is arguably one of the biggest unanswered questions in modern astrophysics. The math for their growth rate simply does not align with the age of the universe.
So what's the running theory?
Well, one leading hypothesis is the direct collapse of massive primordial gas clouds. Basically, in the incredibly dense early universe, massive clouds of hydrogen might have just bypassed the star phase entirely.
Oh, they just collapsed straight into black holes.
Exactly, forming these massive seed black holes that were already tens of thousands of times heavier than the sun right from the very beginning.
That makes sense. But the text also brings up primordial black holes as another potential piece of the puzzle.
Yes, which are fascinating. The idea is that fractions of a second after the Big Bang, the universe was so chaotic and dense that localized quantum fluctuations, basically random super dense pockets of matter, were squeezed by the universe's own expansion pressure.
Squeezed until they just collapsed into black holes.
Right. And these could have ranged from microscopic anomalies to massive gravitational anchors, potentially serving as the building blocks for the supermassive monsters we see today.
But the text notes that those are still unconfirmed, right?
Yeah, finding a primordial black hole would revolutionize our understanding of the early universe, but for now, they are strictly hypothetical.
Okay, so primordial black holes are hypothetical. But what is definitely not theoretical is the extreme physical effect these things have on the universe around them.
Oh, absolutely. The distortion of localized space-time around an event horizon is profoundly hostile.
Hostile is such an understatement, because knowing there's a 4 million solar mass monster in our galaxy makes you wonder what would actually happen to a person if they got close to that kind of gravity.
Well, if you were falling feet first toward a stellar mass black hole, you would experience something called spaghettification.
Which is objectively the coolest scientific term ever coined.
Yeah.
But the physical reality of it is horrifying.
It is grim, yeah. It all comes down to the gravitational gradient. Because a black hole's mass is compressed into such a tiny point, gravity gets dramatically stronger the closer you are to the source.
The inverse square law.
Exactly. So the gravitational pull on your feet, which are just a meter or two closer to the singularity than your head, would be exponentially stronger.
So the gravity of your feet is pulling way harder than the gravity at your head.
Right. And the differential in that pull, the tidal force, would actually overcome the electromagnetic forces holding your body's molecules together.
So you would literally be stretched vertically and compressed horizontally.
Drawn out into a long, thin stream of subatomic particles long before you ever actually cross the event horizon.
Honestly, nature is terrifying. But the stretching of physical matter is only half of the weirdness here, right? Because general relativity tells us there's an even weirder effect involving time.
Oh, definitely. The immense mass of a black hole creates a deep gravity well that physically stretches the passage of time itself. It's called gravitational time dilation.
Right. So let's try to visualize this for everyone. Imagine space-time as a three-dimensional grid. A black hole drags that grid down into this infinitely deep funnel.
Yes, a very steep funnel.
And the deeper you go into that funnel, the more warped the grid lines of space and time become. So if you are falling toward the event horizon, and I'm watching you from a distant, safe spaceship, our clocks basically unsync.
Completely. To you, the person falling, your internal clock ticks normally. You wouldn't feel time slowing down at all.
Okay.
But the light reflecting off of you has to fight its way out of that immense gravity well just to reach the observer. And as it fights that gravity, the light waves are literally stretched out.
Which is why the visual information takes longer and longer to reach me.
Exactly. From the distant perspective, you appear to move in extreme slow motion, eventually freezing entirely right at the boundary of the event horizon. And as the light stretches into infrared and radio waves, you slowly fade to red.
So to me, you're playing in super slow motion.
Mm-hmm.
But to you, falling in, you look out at the universe and what do you see?
You see the exact opposite. The light from the outside universe is falling into the gravity well with you, gaining energy. So you would essentially watch the history of the outside universe fast-forwarding in front of your eyes.
It's just mind-blowing. Time dilation is so counterintuitive. But I want to shift gears for a second, from sight to sound.
Oh, the sonification.
Yes. The text mentions that space is mostly silent because sound needs a medium, right? It needs air or water to vibrate.
Right.
But scientists have actually figured out a way to translate the physical ripples around black holes into audio data.
Yeah, it's brilliant. They looked at the intracluster medium, the hot soup of plasma that fills the space between galaxies in a cluster.
Like the Perseus cluster.
Exactly. The supermassive black hole at the center of the Perseus cluster sends out these massive pressure waves as its jets just slam into the surrounding gas.
And those pressure waves are functionally sound waves.
Yes, just with a wavelength so incredibly vast that their pitch is millions of times lower than human hearing.
Right. But by scaling those frequencies up by something like 57 or 58 octaves, scientists converted that data into a sound we can physically hear.
And it sounds exactly like you'd expect a black hole to sound.
It is this deep, unsettling, cosmic groan. You couldn't hear it by taking your helmet off in space, obviously, but it's a direct sensory translation of the extreme physics happening out there.
It really grounds the abstract math into something you can feel.
It really does.
Yeah.
So, okay, we've mapped the anatomy, the time distortion, the spaghettification. But this leads to kind of the ultimate structural question regarding a black hole's life cycle.
Right. The question of whether they are eternal.
Yeah. Because if a black hole perfectly traps light, infinitely stretches matter, and slows down time, Does it just sit there permanently? Can a black hole actually die?
Well, for decades, general relativity suggested they were a one-way street. They could grow by accreting mass, but they could never shrink.
Just eternal monuments in spacetime.
Exactly, until Stephen Hawking introduced quantum field theory into the equation and completely shattered that assumption.
Ah, Hawking radiation.
Yes, Hawking theorized that the event horizon is not actually a static, quiet boundary. It is bubbling with quantum activity.
Because empty space is really empty.
Right. Empty space is constantly generating pairs of virtual particles, a particle and an antiparticle. They pop into existence, immediately collide, and annihilate each other
And this just happens everywhere in the universe, all the time.
constantly. But Hawking realized that when a virtual particle pair forms exactly on the razor's edge of an event horizon, the extreme gravitational gradient can pull one particle past the boundary into the black hole.
While the other particle gets thrust outward into space.
Exactly, and because they didn't annihilate each other, the universe has to balance the energetic ledger.
Oh, so the particle that fell in essentially carries negative mass energy.
Yes, which literally subtracts from the black hole's total mass.
Yeah.
And the particle that escaped becomes real radiation, Hawking radiation.
Meaning that over incomprehensible timescales, a black hole is slowly bleeding its mass away into the void, particle by microscopic particle. They aren't entirely eternal.
No, they aren't. Granted, a supermassive black hole would take a Google years to fully evaporate. That's a 1 followed by 100 zeros.
That is, I can't even process that number.
But the process accelerates as the black hole shrinks, eventually ending in a massive flash of high-energy gamma rays when the singularity finally loses its gravitational grip.
So, what does this all mean, though? Because the source text admits no direct observation has actually confirmed Hawking radiation yet. But if it's true, it introduces a profound conflict.
It creates a massive paradox in physics.
Right, because if we connect this to the bigger picture, we know that everything a star was made of, the carbon, the hydrogen, the complex quantum states of its atoms, was crushed into the black hole.
And over billions of years, it might swallow planets, asteroids, all containing highly specific quantum information.
And quantum mechanics insist that information can never be destroyed, right?
Exactly. I mean, you can burn a book, but theoretically, if you had a perfect computer, you could track the smoke, the ash, the heat, and reconstruct the words. The information is scrambled, but it's preserved.
But the rules of the event horizon dictate that nothing can ever escape a black hole.
Yeah.
So if a black hole eventually evaporates into total nothingness via Hawking radiation, which is just random, featureless thermal energy, what happens to all that physical history?
Where does the information go? Does the universe just permanently delete it?
Which would violate the core tenets of quantum mechanics.
Exactly. Or is the information somehow encoded in the Hawking radiation, scrambled beyond our current mathematical comprehension? This is the information paradox.
It's the ultimate clash between general relativity and quantum mechanics. But before we wrap up, there's one final really provocative theory trying to solve this paradox that the text mentions.
Oh, the holographic principle, yes.
Yeah, it suggests that the information isn't actually lost inside the black hole because it never truly falls inside.
Right. The math of black hole thermodynamics shows that a black hole's informational capacity, its entropy, is not proportional to its three-dimensional volume inside.
It's only proportional to the two-dimensional surface area of its event horizon.
Exactly. Which implies that every physical attribute, every quantum state of the matter that fell in, is left plastered like a two-dimensional barcode right on the surface of the event horizon.
So as the black hole evaporates and that 2D surface area shrinks, the information encoded on it is slowly peeled off and carried away by the escaping radiation.
Yes. The interior volume of the black hole might not contain the information at all.
Which is just, it implies that a complex three-dimensional reality can be fully encoded on a two-dimensional boundary.
And if that is true for a black hole, physicists argue it could be true for the universe at large.
That is wild to think about. The 3D reality we experience every day might just be a holographic projection of information stored on some distant 2D boundary of the cosmos.
It forces us to question everything. The text leaves us with these massive mysteries. What really happens inside a singularity? Do wormholes exist?
Can black holes merge? Which, by the way, they totally can, creating ripples in space-time called gravitational waves.
Right. By trying to understand how a dead star collapses, we might have accidentally stumbled upon the source code of reality itself.
It's the ultimate testament to why we study the extremes of space. Well, we've taken you on quite a journey today. We've charted the violent collapse of stellar pressure cookers into singularities.
We navigated the magnetic friction of accretion disks.
We watched time freeze at the edge of the abyss and talked about the horrors of spaghettification.
Only to end up realizing the universe might just be a hologram printed on an event horizon.
That's a lot to chew on. So as you go about your day, think about that paradox. If a black hole evaporates into nothing, where does the history of all those swallowed stars and planets go? Does the universe really have a delete button?
It's a puzzle that's still keeping the brightest minds up at night.
Thank you so much for coming along on this mind-extending deep dive. Keep questioning the physical world, keep pushing the boundaries of what makes sense, and keep looking up. We'll see you next time.